Goodness. Go. All right, ladies and gentlemen, welcome to the March 2023 DAS meeting. We got a few things we're going to be doing today. First thing is any new members, people who haven't been here before, want to introduce themselves. Let me turn that around real quick. Hello, how you doing?
Hello. Hello. I'm should I stand?
Yeah, sure.
I'm Rob Comcheese. I just joined. I came last Tuesday. I met some of you guys. So and then decided to come here. I brought two friends with me, Fran and Darren.
All right.
We're not members yet, but we might be able to convince them. So.
Cool. Fantastic.
Welcome.
So we better make this good.
Yeah. Yeah. I just got a telescope. I barely used it maybe like 3 times. So I'm very new to this. So
cool. Very exciting. We will help you out. Very
good
cool.
to be here.
Right. All right. Anybody else? Is that it? Oh yeah.
Bobby, too fast.
He's been here. Yeah, he's been.
Waiting for Anthony to just do it. Work.
Yeah, I think it was February.
Yeah.
But you've been here a lot.
Yeah.
I forgot you were here.
First formal meeting, yeah.
That's good. Oh, the camera's like not working. There we go. What happened there?
I don't know.
I think I don't think it's true.
Yeah,
All right.
This is my cameo appearance, right?
Let me share the screen real quick because one thing to share here, upcoming next month, we have the NEAF Expo, and I do believe that is before our next meeting. So hopefully NEAF is back on and we get to go and have a great time. For those of you who have not been before, it's a large exposition. There are tons of telescope vendors there and eyepiece vendors and all sorts of exciting things on display. There's booths about making your own telescopes. There's booths all about different projects you can get involved with in astronomy. It is the largest astronomy expo in the world. And you can go around and check all sorts of booths out, and they often have some telescopes on display outside to do solar observing. And they let you look at the sun. That part's pretty fun too. And they often do talks with famous speakers and things like that. So you can check out NEAF's website and find out all about the exciting talks and things that they have planned. So hopefully it's back on. A couple of years ago, it was excellent, but it got canceled the last couple of years and remote due to COVID. So hopefully everything's back the way it was before. Crossing fingers.
It's about 2.5 hour drive.
I think that's about right. Yeah.
And in years past, often a handful of DAS members would kind of carpool. So I would encourage, if anyone's interested in going, use the groups.io and maybe form some carpools. So
Definitely.
what's that? No, it's in New York. Outside of New York City.
Just north of the border with New Jersey. Yeah.
Yeah.
Yeah, it was falling down.
So with all the rockets being shown on that advertisement, do they sell rockets too?
I don't actually think so.
False advertising.
Yes, I'd say so.
But they do have talks about them.
Oh, okay.
They certainly could. Yeah. Good question, man. All right, so the next thing I'd like to tell you about is we've been working really hard to get the telescopes in the Solon up and running with the new technology that we've been purchasing, working on, and upgrading. And we actually have started doing some observing with it. And we're hoping as the weather's getting nice, we can run some training sessions. We've been making some videos about how to use the equipment and gear. And we're hoping to get people trained on how to access the building, how to use the system, and be able to use it the way we used to. So that's going to be really exciting. Yeah. So please stay tuned and we will help you guys get started with that.
So Rob, in that vein,
Yes.
how do we get into Mount Cuba? Is that?
So yeah, there's a process involved with that. And anyone who comes would get trained in that.
Okay.
So the first thing, of course, we have to get approval for the particular people in whatever training course we have so that they can be on the approved list for accessing the grounds. They would not have access to the building. They just have access to the grounds.
Right.
And once they're on that approved list, they'd know how to use the code to enter the gate, and they'd know how to use the buddy system to do things properly on the property. We
No
haven't discussed it.
kayaking, right?
No kayaking. Where's the bathroom spot? It's a great question. Yeah. So, yeah.
I didn't think about that.
Yeah, it is interesting. Yeah, but we will train you on all those details for whoever decides that they'd like to join our program. But we haven't fully finalized it yet. We're still not quite done. We purchased a couple other things this evening, or sorry, approved the purchase of a couple other items this evening so that we can hopefully finish that up and get it ready. So we're hoping this spring, and it's now spring, so soon.
And actually a little peripheral to that, because it was mentioned. It is entirely possible to actually get a key to the building itself. That actually more plays into becoming a Mount Cuba, either technical or educational associate. A little off topic, but it does relate because there is a way that, you know, DAS members can get a key to the building. If anyone is curious about that, I don't want to go into it too much. Just reach out to one of the DAS board members and we'll let you know what it's not an automatic. There's a give and take involved. But we can talk about what that is.
Yeah, you need an extensive background check.
But I do want to point out that it ties into something we've been talking about the last several meetings, and that is becoming an education or technical associate of Mount Cuba. And, you know, just last night, I did a program on the Big Bang for a group of about 25 people that came here. We had a great time. They were very excited and they're interested in getting more involved in astronomy. So it's very cool and you should try it. It is a great time. So talk to one of us or talk to Kim about getting involved. Next item is the election. So this May, we are going to be having an election for the board members at large. And if you are interested or excited to get involved with the DAS board and have a say in all these exciting things that we do, you could certainly do that. So just contact me. Again, my email is in the focus. I'm Rob Lancaster, I'm the president. So you can contact me or one of the other board members about getting involved and deciding that you'd like to be on the board. So you just have to run for office, basically, right? So that again is going to be this May, and at the April meeting will be the last chance you'll have to decide you'd like to run. So you've got for another month, and then you can make that decision. Okay. Next item is the dinner meeting. We got a couple announcements about that. Jeff, you want to talk about that?
So as I mentioned before, the DAS May dinner meeting is back on. After a 3-year break, plans are well underway. For any new members, because we actually have a good amount, effectively for the meeting in May, we will not be at Mount Cuba. We will actually be at St. Thomas Episcopal Church in Newark, Delaware. And it's a really, really nice event. We try to bring in a speaker. It often ends up being somebody from NASA or, you know, a nice engaging speaker. We also serve a meal. Sometimes we give awards to DAS members or other members of the public. There's a couple of awards that we have a history with. And all in all, it's a very, very nice evening. The website for that event is now live. There is a link to it in the current focus, and we will probably create a prominent link to it on the homepage of the DAS website. On that page will be all the details about the location, the time, the menu, and there is a link to register. Despite the fact that food now costs 3 times what it used to, we're keeping the price at $20 per person. That includes the venue, the speaker, the meal, the camaraderie, spending time with me. Worth at least $20, I would argue.
You're gonna have to pay someone.
Right. My mom used to have to tie a pork chop on my neck to get the dog to play with me. So it's a really nice event. Again, if anyone's not been to a dinner meeting is great and is curious about it, just talk to one of the other members. That's the word. One little caveat: if you go to the website, we have not yet announced who our speaker is going to be. And that's because we don't quite yet have one. We normally have the speaker by this point. It's been a little bit tricky. I'm not going to lose a whole lot of sleep over it, but I put out there if anyone has someone that they think could be a good speaker for that event. We do strongly prefer that someone would be there with us in person to give an in-person talk, rather than tying them in over Zoom. And there will be no Zoom counterpoint. Like, it just doesn't make sense for that type of an event for DAS members to join via Zoom. It's hard to serve the meals over the camera and all that stuff. So if anyone has exactly right. So if anyone's got a good speaker in mind, please reach out. hopefully in the next 2 or 3 weeks, we'll have that squared away. I think that is it.
All right, next, Bill, can you tell us about the AP SIG meeting coming up?
So the next astrophotography special interest group meeting will be Saturday at 1 p.m. on Zoom. Don't have a special topic for it yet, but we certainly will have a variety of photographs, and they'll always have equipment and technique discussion. So it's useful to anybody who's interested in doing astrophotography. Thanks.
All right, very good. Thank
And
you.
the announcement will go out over groups.io.
Oh, perfect. Yep. Thank you.
So
And Mary, is there any announcement for the book club?
Yes, there is. The book club meets next Thursday, March 30th at 7 p.m. via Zoom. We will be discussing The Quiet Zone, Unraveling the Mystery of a Town Suspended in Silence by Stephen Kersey. Stephen will be joining us. He is a very acclaimed journalist who applied a military technique that the journalists apply, where they embed in a community and then investigate and write based on their experience as they actually live with the community they're studying. The Quiet Zone, of course, is Green Bank in Pocahontas County, West Virginia, where many members of the Delaware Astronomical Society have been. This is not as much a book about science as it is about the effects of a scientific entity on a community, and how the common man in the community copes with the ramifications of the science. He covers topics like Patch Adams scandal, white supremacy, Nazis. It goes to the Rockefellers who are down there, the hippies, the back to nature people, the electro hypersensitives who are down there, and all of the rumors attendant to running the government spy center. So it's a very, very spicy. It's probably one of our spiciest, most kind of jaw-dropping reads to date. And so we're very much looking forward to it. It does not read like a science book at all, much to my surprise. And I wanted to just also quickly announce that our April meeting, at the suggestion of one of our most senior founding members, James Cower, we'll be reading an Edgar Allan Poe story, Malanta Tauta, I think I'm pronouncing it correctly, by Edgar Allan Poe. I don't know if any of you have seen the Netflix movie Pale Blue Eye, but Edgar Allan Poe is very much in the zeitgeist right now. People are talking about him. The performance has been acclaimed. This is a kind of a sci-fi story. It's not a detective story. And will be joining us will be Professor Hal Poe, who is one of the Poe family. And he is a renowned expert in the life and work of his ancestor. And we also invited a professor of English from the University of Delaware. He agreed to join us today, Professor John Kebb. And he, there's an association between Edgar Allan Poe and the University of Delaware. In 1843, Poe went to the Newark Academy, which is a building presently on the campus of University of Delaware, and lectured there. So he's part of the history of the University of Delaware. Therefore, there is this local connection. The professor will be joining us, and we're also going to invite English students at University of Delaware as part of our public outreach to join us for the discussion of Malanta Tauta. Thank you.
Okay.
Guests are always welcome to book club meetings.
Very nice. Thank you very much. All right, without further ado, let's
So
continue.
we want to try to, would some,
Oh, they said something was
we
fun.
want to try to
Focus. Yeah, the camera.
give it a,
Let's see if it focuses.
good.
It did autofocus on my hand. Yeah, it just autofocused again. So I think it autofocuses.
okay.
They're saying it's dark.
Maybe.
Yes, it might be. How we looking now, people of Zoom?
Rob just looks really pale.
Yeah,
He-
okay.
Okay.
Maybe a little bit.
Yeah, I think he's got the sun a little.
Your hair looks crisp.
I know a place where you can go.
Looks all right.
Yeah,
Yeah. All right, looks
All right,
fine.
yeah, we'll roll with it. Thanks for the feedback,
Yep, thank you very
people in
much.
Zoom land.
Might be a bandwidth issue.
Yeah, that could be.
Too many bands.
Too many bands. All right, well, let's get started with the next part.
Cool. Actually, do you want, I realize why don't you man that? Because
Okay,
I screw it up more often than I get it right.
now I can do that.
Yeah, so our main speaker for tonight, we are being joined by Dr. Véronique Petit. Dr. Petit earned her PhD up in Quebec City and is now a professor at the University of Delaware. She actually gave the DAS a talk about 10 years ago and is back tonight to share. She does research in massive stars and is going to be talking about those with us here tonight. A little bit of protocol. Véronique said that she's happy to have people interrupt at any point with questions or comments. And I would say that includes us in person as well as the people on Zoom. Rob, you just muted everyone?
Yeah.
Okay, cool. We have muted everybody on Zoom just to keep the audio quality clear. But if anyone on Zoom has a question or comment, just please temporarily unmute yourself. And then please remember to get yourself back under mute. The other little comment, unlike years past, we will not be monitoring the Zoom chat. By all means, I'm not going to say don't use the Zoom chat if you guys want to chat amongst yourselves, but we won't be monitoring it. So if there's questions or comments or concerns that are brought up in the Zoom chat, we won't catch it. So if it's something burning, please just speak up.
Next to the things you can do.
Oh, no, I read that.
Yeah, cool. And with that, we welcome Dr. Véronique Petit.
So yes, I prepared a bit of a presentation, but from my experience in astronomy clubs so far, it can go everywhere, anywhere, right? So I don't feel like I need to go through all of those slides. If some of the stuff is too basic, just say me like, go quicker. If you want me to slow down or go on a tangent, another topic, I'm more than happy to do that. This is basically just little food for thoughts and way to get the conversation going. So feel free to, stop me at any time and ask me more questions about stellar magnets, black holes, and massive stars. So as Jeff said, I'm a professor of physics at the University of Delaware. I'm so not an amateur astronomer, funny enough, right? I started my academic career using 4-meter telescopes and even a 1.6-meter telescope at the Mont Megalithique Observatory. So God knows they don't let the graduate student actually touch those telescopes, which are worth millions of dollars. We had a technician, basically a telescope operator who would move the telescope, right? And we were operating the instruments. So this is how it also worked at Canada France Hawaii telescope, where I've used all of my, took most of my data when I was a graduate student, for example. They don't let you touch the telescope, I can tell you that. So imagine my surprise when, and I'm pretty versed though in spectroscopy and spectropolarimetry, which is the measure of the oscillation of light. I'm really excited about a spectrograph that is lying upstairs. Yes, Judy got that for me. I'm really happy and looking forward to actually using it for real research. But imagine my surprise when 10 years ago I started teaching at a new place in Florida and say, hey, Vero, you'll be in charge of teaching the observational astronomy class with those, 10 inches meads that we have on the rooftop. And I was like, how the hell does this thing work? So I was learn on the fly, which was very. But so today I want to talk about more of the science of massive stars and what we do, for example, at the University of Delaware in my research group. So let me start. And as I said, it might be, for usually the level of knowledge of astronomy club is quite high because you are giving public lectures to the public on some of these topics. So by all means, tell me to speed up. If you want to go to the more interesting and exotic topics quicker. But let me start with what are massive stars?
Big ones?
big ones, right? Exactly. Stars. Stars that are massive, okay?
Tom Cruise.
Pretty much.
Yeah.
Right, yes, yes. I'm thinking, I would go for George Clooney.
Okay, fair enough.
But actually, no, who's Aragorn in Lord of the Rings? That's my new favorite actor. It's
Oh.
so nice, right? A superstar, but actually a very nice person apparently.
Fred would know.
But being massive is not necessarily the best describer or what's the most extraordinary about massive stars, funny enough. And basically massive stars are object of power, okay? And when I talk about power, I don't think about, you shall not pass, reference to the rings here. But more powers in the physics sense, okay? So in physics, power has a very, very specific meaning, okay? It's an amount of energy per amount of time. And you actually know intrinsically what power is in the context of physics. If you ever bought light bulbs, whoever bought light bulbs? Yes, yes. So the unit of power are actually watts, right? So you have a sense for how much power is 100-watt light bulbs, right? You can imagine that. So that's the definition of power. So let me tell you about stars. So stars are very, very powerful objects. So if I was to go and buy a light bulb that has the same power, energy per unit of time, per time interval as our sun, this would be the light bulb I would go and buy. Okay, so that's 26 zeros after the one. Okay, that would be a really, 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 really large amount of watts. So it's 10 to the 26 watts. Okay, so that gives you an idea of how powerful is the sun compared to an object that a light bulb. But when you think about this, if I put a light bulb in front of my face, it's like, oh my God, it's really bright, right? But the sun doesn't look that impressive. It's all over there up there in the sky, right? How can it be so much more powerful than the light bulb that you can use for reading, for example? Think about it, right? What do you feel about the sun? You can get a sunburn. You can read during daytime without a light, but at night you need an actual light bulb to be able to read your book. Okay, so why is that? That's because the sun is very, very, very far away. Okay, in the grand scheme of things. So let's think about a little scale model, and there's already one there on the wall that some of you might know really, really well. So I'm going to go this quickly, but I usually take a sun that's a little bit smaller than the one that's on the wall here, and I think about a football. I'm married to an Englishman, so football is soccer. Okay, so let's say soccer here.
Yeah.
Go Seagulls, that's our team in Brighton. So if the sun was the size of a soccer ball, basically Jupiter, which is the largest planet in our solar system, and can somebody point at Jupiter on the wall right there? Behind? That's not the one with the ring, the one next to it. There you go. Right, so that gives you an idea of a scale. So we have a soccer ball and a ping pong ball would be Jupiter. And usually I bring peppercorns with me, but I keep losing them everywhere. And on this scale, the Earth would be about one little peppercorn, okay, compared to my soccer ball. So that gives you a good idea of scale, and we have it on the wall here. But it doesn't give us a really good handle on the distances, right? Because all of those drawings that are on the wall here and on my slide, they're not to scale in terms of the distance between those objects. So if I was to give my virtual peppercorn to somebody, who wants my virtual peppercorn? And here's my virtual ball. There you go. There you go. Good. All right. So where do I need to put that peppercorn in order for the whole model to be to scale?
Probably Newark.
Yeah.
Actually, it's not that bad, right? But if you would stand up, do you mind? Thank you.
Can you drive to Newark?
Okay. Further.
She's not using my 50-inch.
There you go. That's about right. Okay. So imagine that's us on this little peppercorn over there, and this is where the sun would be if everything was to scale. Thank you very much. I'll get for that. I'm teaching an intro astronomy class at the University of Delaware right now. And we're talking about scale models, and you're thinking about the map, how distance can be represented in a map. When you say, okay, 10 kilometers is 1 inch on the map, it's not real. It's not a real, 1 inch is not equal to 1 kilometer, sorry, 1 mile. Canadian kilometers, right? To 1 mile. And we make those equivalency, those models, like an architect model. And then the students, I made them, put the Earth on the moon and Post-it, and then the moon on the other Post-it, and made them calculate an assignment, how far away should the two be? And they were sending me emails like, Dr. Petit, this can't be right. It doesn't, I get 7 feet. It doesn't fit on my piece of paper. And I was like, cut the piece of paper. Stick it on a wall, right? And people were like, whoa, this is really fun. So space is much bigger than what we think when we try to put everything to scale. So the Earth, the little peppercorn over there, is quite far away. So let's think about power for a second, okay? So imagine that on this little peppercorn over there, there's a picnic table, okay? So imagine a picnic table on a peppercorn, maybe really, really small. And let's say that the area, right, the surface at the top of a small picnic table is about 1 meter square, okay? The amount of light that will from the sun arrive on just that little piece of 1 meter square would be about, how many is that? About 10 light, the equivalent of 10 light bulbs. Okay, so the sun is very, very powerful, that even at that really, really large distance, it still gives us a lot of energy. And that's true to all of the stars. Okay, so you know that the sun is a star and the stars are suns, right? But why do they look so different? Right? If you think about our sun, big yellow ball in the sky, and when you look at the stars, mostly at night, they look like tiny, tiny little dots. If they are all the same thing, they're all stars, why do they look so different? Yes, we'll come back to standard candle as well, right? So that means that if they're the same, the stars are stars, what does that make? What is making the star look so different? They're really, really further away, right? And talking about standard candle ratio, just at that moment. And it's the same when we think about cars, right? So we have a car, 2 cars, and one of them is like right on the other side of the intersection, and there's the other one really further away. We know it's far away because it's dimmer, right? It looks dimmer. And it turns out that I'm just gonna put, I don't put a lot of equations, I promise. Okay. So basically, the brightness, okay, what we perceive with our eyes or a detector or a telescope is proportional to the distance, the inverse of the distance. So the farther away, the dimmer it appears. But not only the distance, but the distance square. Okay, so it's even worse. When you put something further away, it looks even dimmer because of that that square. Okay, that's the distance multiplied by the distance. Okay, so it looks very, very faint. So just to come back to the stars for a second, if we have our sun here, my soccer ball, we have the peppercorn. Where do I need, if I have a second soccer ball, where do I need to go in order for this to scale be the distance between us and the nearest star?
Now we're talking at least Newark, maybe New Jersey.
Okay, so I would go outside this building,
Yes,
get in my car,
yes.
I'm gonna drive to Philly. I'm gonna board a freaking plane. And I'm gonna go all the way to Florida.
Miami, that makes sense.
And that's the closest star to our sun. Okay, so imagine there's one soccer ball here. Well, actually, this is more the scale. I kind of fudged it a bit with soccer ball. It's more like something that's more grapefruit, right? Smaller. I still have to drive or fly all the way to Miami. Okay, the rest of it is empty of stars. It's incredible. The stars are so freaking far away that it's absolutely insane. That's why they look very, very dim compared to our sun, because our sun, we said, oh my God, it's so far away that I have a little peppercorn, but it's really interface. compared to the other stars.
Is that why you were working in Florida?
Oh, yeah. Then it was too hot Canadian. I had to-
Right.
It was nice. It was -30 over Christmas in Quebec.
Mm.
So let's talk a bit more about stars, right? So we know why they're dimmer, but if we look at them, they don't look all the same, do they? So which constellation? Oh, I was about to ask which constellation is that? It's like says Orion, but I'm sure that you all recognize our very famous Orion. What is different about the stars in this image? The color is different. What else is different?
Diameter.
The diameter, the size. Okay, what else is different? Different?
Proximity between other stars.
Yes, yes. Mhm. What about the dimness? Are some bright and some dim?
Sure.
So there's different things in here. The one thing I'm going to talk about first is the size. Okay, the size here is fake. It's an artifact of the cameras. Okay, it's the same that if you take a photo and there's a light source, and sometimes it saturates in your camera and you get like a big splush of white in your photos. This is what happens here. Most of the stars we cannot resolve. We cannot tell, we cannot, like our sun, for example, we can tell there's a disk, but all of those stars, they're unresolved and they just look big because they saturated the camera. Okay, but the brightness is real. The ones that are bright, and the ones that are dim. There's different distance between all of the stars, but it's quite interesting, right? So if we look at the brightest stars,
There is a
They
pointer,
quite-
if that would be helpful.
that's fine.
There you go.
Like that pointer.
Cool.
So if we look at this, there's the very bright ones are quite sparse, but if you look at the dim ones, and there's a lot of them, right? In this image, and also the color is different. So let me start with the color. And the color tells us something very important about the properties of stars. So this one's Betelgeuse, this one is Rigel, one is orange, one is blue. Okay. And this is what, okay, this is completely driving me insane, is the name of the freaking light bulb colors. Okay. Why warm white, cool white, and day white. Okay. So cool and warm. But if we look at actually the temperature, so if you buy a light bulb, sometimes they're going to give you a temperature in kelvins. And this is what it looked like. And this works the right way around, right? A small number means cold and a large number means hot. So the people who were naming things messed it up. I understand the concept, but in fact, redder light comes from light sources that are colder than blue light. Okay, so that's a little bit weird to us. But if you think about a flame, what is the hottest part of a flame? The blue part, right? So it works in some way. And I think it comes from water, right? We think water's blue, water's cold. Maybe that's why we have that impression that cold is blue and hot is red, when in fact, in terms of light, bluer means hotter.
I had a student in a program I did who said, well, the stove is red hot.
Mhm.
So that must be as hot can be in
Exactly.
his mind.
I know, but if you keep like warming it up more, it becomes white. It's such a pure white. So yes, I know.
Yeah.
So if we think about Rigel and Betelgeuse, which one is the warmest? It's gonna be Rigel because it is. There you go. So I'm going to talk here about two of the important characteristics. We talked about the colors, but we were talking about power, right? And the amount of energy per second and how bright an object can be. So there's the distance that we need to take into account, right? So if you have two things that have the same intrinsic power and you put one very, very far away, to us, it appears dimmer. One way around that is to talk about star clusters. So star clusters are a group of stars that are all at the same distance from us. They all packed together and they're physically actually next to each other. So if we take one of those star clusters, so this is, you probably know better than me, Omega Centauri. That's a Macy object, right?
Yeah.
That's M.
No, maybe so.
Is it?
That's cloud, so unless you wouldn't see it.
So this is an image of one of
I'm
the
sorry,
clever-
Florida. Yeah, no, you can see it from here. Yeah, barely.
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 in the trees. If you cut a couple of trees, that would work. It was beautiful. We were at SAT last weekend, no moon, totally, you know,
Oh, wow.
no, that cold, it was freaking cold, but yes, I haven't seen the Milky Way in a long, it's been a while since I've seen the Milky Way, so I was like, oh, this is very nice. And a big, big shooting star right in the foot of Orion. So.
Oh.
Okay, but here what I'm gonna do is take a little zoom in. So this is an image that's been taken by the Hubble Space Telescope in a little portion of that globular cluster. Okay, the colors are still fake a little bit. So blue on it, that blue to our eyes, they would appear more red and less red. But then they color coded this image so that it will show the difference in color a little bit better. And astronomers, so we try to disentangle two things, right? There's the color and there's the brightness of the objects. And what we like to do in at least astronomy is to sort stuff out. So we're gonna do like in a, you know, the photo albums in elementary school, like put yourself in order of size for the photo, right? This is what we're gonna do. First, we're gonna tell, okay, all the hot star go to one side and the cold star go to the other side. So it's gonna, if we do this, it's gonna look like this. Okay, and you will notice that hot is on the left and cold is on the right. Right, versus if you think in temperature, small numbers should be on the left and large numbers should be on the right. Go figure, that's, who knows about the magnitude? Magnitude system? That's the fault of the magnitude system, that's why it's. So once we got all of this, we sort them out in temperature. We're gonna tell them, okay, all of the dim ones go at the bottom and the bright ones go at the top. And it's gonna look like this. So if you notice, if we do this exercise, not all combination of temperature and brightness are possible, right? Most of the stars are gonna end out on that band in the middle that we call the main sequence, with a few stragglers here and there, okay? So that's quite interesting. And this is a diagram. When we do this exercise, so this is a romanced version of it from textbooks, right? Where this is what we call an Esperon-Russell diagram, HR, because nobody can pronounce it properly. And we have hot and cold, and then dim and bright. So basically the scale, the vertical scale is power, the power that we encountered before, the amount of energy per second. Okay, because all of those stars are at the same distance. So if we look at this, what's the next one? I was like clicking my slides. What's the next one? There you go. So we're gonna just talk for a second about all of the stars that go in that diagonal band, which is called the main sequence. Why are they there? Okay, why is it not possible to have different combination of temperature and power? And this has to do with what they're doing at the moment. So these stars, the main sequence, are stars that are burning. We say burning, it's not really burning. It's nuclear fusion in their core. So there's hydrogen that get mushed together and transform into a new element that's called helium. Okay, and this is what power stars. It's a nuclear reactor. And all of those stars right now are doing that, and including our sun in their core. And this sequence that we see is basically an order of mass. So the less massive the star, it's going to be redder and have less power. Our sun is about here. And if you have a star that has 100 times the mass of our sun, for example, it will be hotter and have more power. Okay? So this is basically mass is what decides where the star is going to be in that diagram or on the main sequence. And it's going to stay in that position for as long as it's able to fuse hydrogen into helium in its thermonuclear core. Okay. Let me go back to massive stars, right? So massive stars, woo, can be like 100 times the mass of our sun. Wow, right? Let's look at the power. A star that has 100 times the mass of our sun has 1,000,000 times the power of our sun. Okay, so the increase in mass, it's impressive. It's 100 times more massive, but it has so much more power. It's quite, yes, it's basically a a Fiat versus a huge Mustang, right? Or what's the one with the big wheels again?
Monster Palmer.
Monster truck. There you go. So just to give you a little example, remember this, what I was talking about earlier? The sun and like, oh my God, the sun like is so powerful from all the way over there, right, with a peppercorn, that if the picnic table on the peppercorn has an area of 1 meter square, it would be the equivalent of 10 light bulbs, 100 watts light bulbs. But if we were to now replace our sun at its current location with a massive star, this would be the amount of light bulb that would fall, that would give you the same power than the massive star. Lots of power. And it's probably what's going to happen. Mhm. So massive stars are the thing that we study in my research group, and I'm really, really fascinated about for many reasons. So first of all, so I'm going to go back to, this is an HR diagram. So you see, I'm going to more and more technical graphs, okay? But still in the hand-drawn thing where we have our HR diagram again, and the line represents that main sequence. Again, the same graph, but just in a sketch format. And once again, what makes what decides the star position on that main sequence? Which characteristic? The mass. Very good. There you go.
And time?
No time.
No time.
No time, as long as you're burning hydrogen into the core.
So
But can you burn hydrogen forever?
the numerator was power, the denominator was
Temperature.
temperature. Okay.
Temperatures, yes. So it's gonna, our sun's gonna stay roughly, it's not exactly true. As the sun burns more hydrogen into helium, it's changing its composition, the structure of the sun changes a little bit. It will get a little bit colder and a little bit more luminous with time, tiny bit, but it's not gonna move noticeably up or down the main sequence during its lifetime. Okay? But is it gonna stay there forever? If you have a car and you have fuel in the tank, can you drive forever? Yeah, that's a finally gonna run out of fuel. So then interesting stuff is gonna happen to our sun or stars in general. Okay, but no worries, it's gonna take a little while for us, and about like 10 billion years for the sun. Okay, and we're we're halfway through the fuel tank, so we still have another like 5 billion years to go. We're good.
5 million or billion?
Billions.
Sorry.
Billions
Yeah, that
with a B. Mhm. Yeah. A million years, so I mean, it's still quite long.
Would be almost touching Earth.
What's that?
A blue star would be touching Earth possibly. Because it's gonna
Oh.
grow really big.
They're not that big. Red supergiant are much bigger,
Okay.
would totally be touching the Earth.
Yeah.
At some point, but massive stars are usually a bit more compact. So the more right you go into this diagram, the biggest the star has to be.
Okay.
And it has to do with the laws of light. Basically, if you have something that's hotter in the same area, it emits let's say you double the temperature, you 2 times 2 times 2 times 2. So you 2 to the 4th power increase the power. Sorry, I said power twice here. Right? So it's a bit confusing. So that means that if you have 2 stars that have the same power, but one of them is colder, it has to be bigger.
Okay.
So that's why, so those of you might know about red giants, which would be over here in this diagram. They have, let's say, the same power than the massive stars, but in order to do that, if they're colder, they need to compensate by being bigger. Okay. Same for the white dwarfs. Know about white dwarfs? You probably heard about Judy's, research about white dwarfs. So they're really, really small, but really, really hot. So they're very, very dim. But because they have the same temperature of massive stars, but they are much dimmer, they need to be much smaller.
Where would a neutron star be?
Not in this diagram, because they're not sure what the temperature is.
Okay.
I hate to skip ahead, but say this supermassive black hole in the middle of our universe. I'm sorry, our galaxy. Would it reach us in its event horizon?
No, so the event horizon of the supermassive black hole in our middle of the galaxy is So one solar mass is 3 kilometers. I'm so not the galactic astronomers. What's the mass of our black hole? 15 million. So you think 15 million kilometers in the grand scheme of things is not very, very large. And at the scale of the galaxy, which is 100,000 light years across. And light years to kilometers.
A lot.
Okay, you will laugh, but astronomers, we use units, and when we do all of our physics and stuff, we don't use SI units, so there's the imperial units, right? Feet and pounds and stuff, we don't use that.
Logical ones.
Then there's the scientific units, meters and grams, and kilograms per second and stuff like that. Okay, which makes sense, but for some reason, astronomers use the CGS system, which is in gram centimeters a second. It's like, why the hell are we using centimeters to talk about the size of freaking stars? So I know things like the radius of the sun, or the astronomical unit in centimeters, and I was like that.
So the sun to the supermassive black hole in the middle of our universe, galaxy, right? If it was in our solar system,
Oh, okay.
that was the question. I was asked. That's totally different.
Yeah.
Would we be in the event horizon or would Mercury?
Actually, are you gonna make me do math on
Remember, this is being videotaped, so don't mess up the math. Yeah.
3 kilometers, right? And we said it's 15 millions. Millions is okay, next let's six, right?
Six.
Six, right? So let's do this. So we're gonna end out with
45 times 10.
yeah. We're just gonna round it out to 10 to the 6 kilometers. Astronomical unit, so that's the distance between the center of the sun and the earth. Oh, it's 10 to the 13 centimeters. I'm gonna put that in kilometers times. No, it's kilometers. 10 to the 8 kilometers. Is that right? Can somebody double check that one? No, you don't have Siri?
Sorry.
I need 3 million.
About right. That's about right.
That's about
3 million miles.
That's about right. Okay. So it wouldn't touch the earth. It wouldn't touch the earth.
But she was counting her breath. Okay, she was counting her breath. Okay.
Above, if I start counting and above like 10, I need to switch to French. Yep.
Does the heat travel farther if a star's hotter? Like the heat of it?
Okay, that's a tricky question, right? What is heat?
Like
vibration.
Okay, so think about heat. If you put your hand, so which one would you rather do? Put your hand in a pot of boiling water, or put your hand in the oven at 300 Fahrenheit to get the cookies out? Which one would you rather do?
The latter.
But the oven is hotter.
Right. But yeah,
You don't have the.
thermal, what's the word?
It's a density that's
Density, yeah.
different, right? The density of particles and things like that, which is what we perceive as heat, might be different than what you talk about in terms of heat or light in space, where the gas is very, very not dense, right? So the same way that I don't mind putting my hand in the oven when I get the cookies out, because even though each particle, so temperature is a measure of how fast the particle are. The camera was not in here. Right? And so the temperature, like in Kelvin, right, or Celsius, is if you have something that's hotter, the particle are going further, quicker. But if you don't have a large density of particles to hit your skin, it's not going to burn you per se. But if we were, for example, to replace Our sun with the massive stars and all that power, yeah, we'd burn to crisps. Because there would be much more light coming through. But the heat, one way to think about this is that light always travels at the same speed, at the speed of light. So if you think about, is it going to go further? Well, no, but there might be a larger density of it at any given distance from the star. Does that help?
There will be more heat, more radiation per square centimeter.
Yes, but it's radiation, but radiation doesn't equal heat. Heat is something that is a property of matter, of stuff, right? Atoms. Light itself doesn't have heat unless it's making this interaction with the atoms, for example, in your body, which what we perceive as heat.
That's the atom jewel.
That was a good question.
Then you got thermal conductivity issues.
Very. Okay. Other questions, while I'm more than happy to go on any tangent.
Yeah.
Don't ask me about the Big Bang, though. I'm a very dumb. I don't like astrology because I'm a very down to earth person.
Yeah.
That's why I study stars.
So is the vacuum in a black hole a colder temperature than the vacuum of normal vacuum space?
Ooh.
I don't think it's.
I don't think we really know what's in it.
We don't know what's in the black
We don't
hole.
have any idea.
And the black hole cannot be empty.
Right.
You go measure with the.
Yeah.
Right? A black hole cannot be empty because it has to have mass.
But
And that mass
if we
needs to be
take what we
very
know about the
dense.
singularity, which is the ultimate gravity, right? So all the energy, which is going to be the heat, is going to suck through there, as far as we know, instantaneously.
Stuff has to fall into the black hole.
It's not an infinite mass, it's the amount of mass that went into it. It doesn't have any different gravity than it happens with the star.
But it can actually
it-
use energy. A black hole can use energy through Hawking radiation as well. That's why we have gravitational wave. I have a little section about gravitational wave a bit later. Skip to that. I have some bits at the end. Yes, we can definitely make sure that we get to that.
I'm sorry to.
No, that's right.
Yeah, I'm just curious, because you have red stars on the right and then blue on the left. Can you have ultraviolet stars?
Oh, yeah, totally.
Like,
So massive stars.
which is-
It's not less likely. The further up you go, the-
Sun included emits light in all different colors.
Cool.
And if you think about different wavelengths of light, this is what we call the electromagnetic spectrum. So what we can see visible, red, blue, green, is a really, really tiny range of all the possible wavelengths of light. So if we go to shorter wavelengths, higher energy, we get ultraviolet. What comes after ultraviolet? X-rays.
X-ray. Oh.
What comes after X-rays?
Yeah,
Rays. Yeah. If we go on the other side, and my husband he studies gamma rays, and we keep saying that the gamma rays range larger than all of the rest of mine.
radio.
But then I tell them like, yes, you get one photon every year. So what goes after visible? Infrared. Infrared light. So our eyes cannot see any of these. So we have infrared, longer wavelength still. After that, microwave. That's what makes your microwave oven works.
And
After
cell
that?
phone.
It's basically, I call this radio. At this point, everything else is radio.
Yeah.
There's some other separation, but it's radio, okay? So if we think about our sun, our star, the temperature, surface temperature of our sun,
That's very nice.
it emits light in a whole bunch of wavelengths, okay? With the majority of it being invisible light. That's probably a reason why our eyes aren't working this way. Probably. But if we take a star that is colder, of the same size, it will emit light like this. Okay, very little blue radiation, UV X-rays, but a lot more in the red part of the spectrum. That's why they look red to us. Okay. If you take a massive star, a blue star, it will emit radiation this way. It's actually going to emit more for the same size. It will emit more visible light than our sun, but it will emit even more blue light, all the way sometimes to the ultraviolet. Some of them, like if you get to the hotter temperature there, their peak in light is actually in the ultraviolet. That's why we built a telescope like the Hubble Space Telescope, because it's much better to look for massive stars, for example, in ultraviolet than in the visible. They're brighter.
Oh, Vera, can you click on the chat?
Yeah.
Somebody said a comment you might want to look at.
Well. It's over here, maybe.
There's like
Oh,
14 million.
Oh, yeah.
She's very patient, thank you.
Ah.
I like that stuff. As I said, each time I come here, I put some slides, but it's just like a starter for conversation. I know the question I got all of it, like, so.
Awesome.
Okay, great. Anything else? Vanessa? Okay. Cool. So what was I saying? Yeah. Stars, right? And so this is where our sun is again. And one of the reasons I like massive stars is because they're the reason we're here. I know we're orbiting a massive, the sun is pretty average, right? We're orbiting an average sun. But if it was not for the massive stars, we would not be here. But massive stars also, and I kind of skipped ahead in my slides. Okay, there's another reason why they're cool. Is that if we see them, we know that where they are is a place in our galaxy or in the universe where stars have formed very, very recently. And the reason is that massive stars are the rock star of the stars, okay? They live fast, they die young, okay? So they have a lot of power, right? Who has a barbecue? BTUs, right? Okay, so massive stars have a lot of BTUs. They also have a larger fuel tank, but they need to use their fuel tank at a much faster rate to get all of that power, right? So what did we say? The fuel tank is 100 times bigger. So here I think I have a number for it. Let's say a star that is 30 times the mass of our sun has a fuel tank that is 30 times bigger, right? But then it needs to output 1 million times more power. So is that fuel tank going to last very long? No, it's like a little economical car, right? So you have a little Fiat with a small fuel tank, you're going to do a lot of mileage on it. But if you have a Mustang, might have a bigger fuel tank, you're going to still run out of gas quicker, especially the way I drive. Okay. So let me put a scale to put the numbers for you here. So let's make the whole age of the universe be 1 year, represented by 1 year. Our sun would live for 10 months. Okay, and the scale is not going to die in 10 months. Okay, but a massive stars would only live for a few hours.
Wow.
Okay, so if you see them somewhere in the universe, that means that in the grand scale of things, you know, in the scale of the whole age of the universe, they only there for a fraction of a second, well, a few hours. So we know that this region, for example, that we see here, 30 Doradus, there's a lot of blue star in there. We know that this whole region, these stars formed very recently, because if this region was old and the stars were old, the massive stars, they were gone. They're already gone. Okay, so they're a tracer of star formation. My other point was that they're the reason we're here. Okay, so at the start of the universe, in the Big Bang, after the Big Bang, there was only hydrogen, helium, and traces of lithium. What are we made of? Atoms of carbon. Where the hell did that carbon come from? Where the hell did the iron, magnesium, everything, potassium came from?
That's sorry.
In the core of stars, right? But our sun, when it's going to run out, so it's currently creating new helium out of the hydrogen, right? Once it's done with the helium, in like 5 billion years, it's going to start doing a bit of carbon and then oxygen, and then that's it. Low mass stars, starting with start our sun, they're not able to fuse, and that's a whole other talk, another story. They're not able to basically go further in the nuclear reaction because they don't get hot enough. And then there's something that counteracts the gravity that's called degeneracy pressure, which is super cool when I teach class, but I'm not going to go into that right now. That will stop the star from collapsing. They're going to become white dwarfs that Judy studies. But massive star, they can go all the way. Okay, they can fuse their carbon into silicon and then silicon into magnesium, everything all the way to iron. They can do all of this. Okay, and then at some point they're just going to explode. They blow up, and then all of these newly created elements are going to go back into what we call the interstellar medium, back into space, and then a new generation of stars is going to form, and we'll have a little bit more carbon, a little more everything. And it's going to go over and over and over and over. Because what did we say about massive stars? How long did they live? Short time. So how many generations, like mosquitoes, right? How many freaking generations of mosquitoes are you going to have in one summer if you left a puddle of water? A lot, right? So since the start of the universe, there's been countless freaking generation of massive stars polluting our universe with new elements that then form into solar system, created planets, people, and footballs. So if it was not for the massive stars, we would not be here. So that's why I think these stars are the coolest, well, hottest stars in the universe. I have a little section here. Oops, there you go. But then my next section is about magnets in space. It's up to you. I can talk a little bit about magnets in space. I can also go straight to black holes. I can do, or I can try to do a bit of both. It's up to you.
Magnets in black holes.
Magnets in black holes. Yes,
Yeah.
absolutely.
Do we know what soul can synthesize elements to?
Sorry,
Do we know what our star can synthesize elements to?
the sun.
Yes.
It's going to be about carbon and oxygen at the end of their life.
Number 4 on the element scale.
Carbon is 6.
Okay,
Yes.
interesting.
And we can see this in the universe, and we know. So how do we know this? How do we know this shit, right? If you look at the abundance of element in the universe, and I don't have a graph here, but it's not all of the elements that are equal. There's some, for example, carbon's really abundant, but then beryllium or lithium are not. So, some of them are more than other. And that perfectly matches what we know of nuclear reactions, right? Not all reactions are possible or going to work as efficiently. And that matched perfectly what we see for the abundance and, of elements around us. Kind of shows how, that we didn't make that shit up, right? So it's quite interesting to see how the physics, like nuclear physics, which is something that's, not necessarily related to astronomy, works. I teach stellar astrophysics, like the physics of stars, and there's some pretty quantum mechanics and that comes into play in here that explains stuff like why Jordan is insane. It's really cool. I love astronomy.
Yeah.
Well,
We use like every little bit of physics to explain a star.
Okay. So what about magnets?
Okay, magnets. Okay. So I study massive stars, but most specifically, I study magnetic massive stars. So our sun is a magnet. Okay. And you see those photos. So the photos to the right at the top, the sun looks weird, right? It's kind of dark and it has like these white weird streak in it. That's a photo that is in the X-rays and the very far ultraviolet. So as I said, a good thing you asked this question is I didn't put this in. I promise we didn't arrange. I didn't pay anybody to ask this question. But our sun doesn't emit a lot of X-rays and UV, right? So in principle, if we look at our sun at those wavelengths, it should appear dark because it doesn't, or dim because it doesn't output a lot of light. So what you're seeing in this image, and especially the, sorry, I can remember.
You're good.
In this image here for severe photo, okay, what you see is gas that gets trapped into magnetic fields and gets heated, like we were talking about heat, and emits light at really energetic wavelengths. Okay, so our sun is a magnet. All of the stars that have the same mass of our sun than our sun are also magnets, and every star that have mass lower than our sun are also magnets. And this has to do with the way this magnetic field is created inside of our sun. So what's happening, it's the way energy gets transported. So we create energy with thermonuclear reaction in the center of the sun. and the sun shines, right? So at some point, some energy needs to go from inside to outside. Yeah. One way of doing this is doing it with the photon, the light. The light can do it. The gas doesn't have to move. They just sit back, relax, put their feet on the couch and let the photon stream around. Okay. This is what we call radiation or radiative zone of the sun. But at some point in the outer layers, the light says, you know what? Pull your weight, damn it. And the gas says, okay, I'm going to help a little bit. So another way to transport energy is to take something that's hot, moving out, and then take something that's cold and move it back in. Okay. So what happens in the outer layers of the sun is you get those rolling motion. It's called convection. It's like boiling water, okay, where the gas is actually helping and physically moving. And that movement is what creates the magnetic field. And you know about this? Who has okay, I'm not in Florida anymore, but we used to have emergency flashlight for hurricanes, right? You have one of those? How does this work? There's no batteries in it. What do? You crank? When you crank, you're rotating a magnet. If you move a magnet, you create electricity, an electric current. This is the reverse way. Charged particles are moving around, and you also need to have the rotation of the star that moves in the other direction. Will create, so you have a current of charges, which creates a magnetic field. This is called a dynamo, okay? This is how we create magnetic field. This is how the magnetic field of the sun is created right now. And it has very cool characteristics. So first of all, it's quite tangled, right? You have these magnetic loop. You've heard of coronal mass ejections, right? These big eruptions where magnetic field bursts open and then reconfigure itself. It's small scale, it's very dynamic. There's these ejections, but there's also the solar cycle and the sunspot, which are all due to the magnetic field of the sun. And so things change in hours, in time scale of hours to days to years, if you think about the solar cycle, okay? And we see that in a lot of all of the stars that are like our sun or less massive. We see all of that activity, the same characteristics, and we think that, hey, you know, if it quacks like a duck, it's a duck. If it, I need to make a good thing. If it's something like a dynamo, it's a dynamo, but then I don't know where the term would go. I need to work on this a little bit. Okay, so we understand this very well. But when we think about massive stars, so another diagram here, this is mass, okay? This is middle of the star in the inside. This is the outside of the star. The color shows you which part is the photon doing all the job, and then the convection, these boiling, rolling motion, doing the job of transporting the energy outside, okay? More like a dynamo, exactly. If you go to more massive stars, then we stop having that convection in the outer layers. The photons can do the job on their own. There's a little bit of convection in the middle of the star, but not for all of stars. There's some stars for which there's no convection motion at all. So what do you say? Dynamo is caused by these rolling motion. If there's no convection, are we expecting a magnetic field? No. Right? Guess who has magnetic fields? The massive stars, right? So these massive stars were not supposed to have a magnetic field. Hold and behold, in the 60s, people started measuring magnetic field. The second one apart from the sun, for which the magnetic field was actually measured, was a star that was completely radiative. So there was no convection. And people just like, what the is this? Okay. And it's very weird because it's not all of the stars. So all the stars like the sun have magnetic field to a certain degree, because it has to do, they all have dynamos. But for massive star, it's only 1 in 10. 1 in 10 massive stars have a magnetic field. These magnetic fields are very different. So it's a big dipole, a big, very simple topology. It doesn't have all of these little tangle and sunspots and things like that. It's also very stable. There's no flares, there's no coronal mass ejection, there's no cycle, no nothing. Everything stays the same. And it doesn't correlate with anything. You couldn't say like, okay, if it's something weird that happens, or it's the convection, the core that creates a magnetic field, well, you would expect all of them to have a big core to have a big magnetic field, or something like that. It's 1 in 10. Like somebody came in and says, look at all the massive stars, like, you have a magnetic field. You do. You don't. Oh, but you do. We have no freaking idea why these magnetic fields are there in the first place. So it's really something that we do not, and that's, so I've been talking, but I have a slide and that's not important. And what's interesting is that we had some ideas, right? People figured this out and say like, oh, it's easy. Let's say that there's magnetic field hanging around in our galaxy. When you form a star, you took all of that magnetic field, you concentrated it, and it was left over. So, okay, then why not all the stars? So it's not a question of where of the characteristic of the star itself, but where it was born that decide whether it has a magnetic field or not. But then we have some stars which are in orbit around each other, same mass, same everything, they form together in a tight orbit. One has a magnetic field, the other one doesn't. Or how can you explain this with, you know, just the magnetic field in the invisible medium? We don't know. Some people says, oh, maybe there was a dynamo earlier on in the evolution of the stars when they formed. Okay, but then why is it not all of them, or all of them with a certain characteristics, all the same range of mass or something like that? We don't know. People start talking about mergers. Oh, maybe two stars. So massive stars, it's pretty cool. They like to come in multiple systems. There's a very large fraction of stars orbiting each other for massive stars. And a lot of them are actually going to merge together during their lifetime. It's pretty cool. And then people say, oh, you know, they're going to merge and like, oof, magnetic field's going to appear. Fair enough. So you would expect massive stars that have magnetic field to be not in binary system, because if they need to merge in order to create a magnetic field, when two stars became one. But then we have one system that we studied that had two magnetic stars in orbit around each other. So that means that, okay, wait a minute, you started with a quadruple system and then two merged, and the whole thing managed to stay in orbit? Quite unlikely, but maybe because it's quite rare to see two magnetic stars or two massive magnetic stars in orbit around each other. So we have no idea. Isn't it cool? There's still stuff we don't know and understand about something as simple as the life of a star.
Are the binaries,
Security.
are the binaries all rotating?
Mhm.
Are the binaries all rotating?
Yeah. Yeah, most star rotates, and massive stars often rotate quite quickly.
Okay.
But the magnetic stars, some of them have orbitals, and massive, okay, really cool. So our stars, like our sun, how do we know how fast they rotate? If you look at the sun, how can you tell? Right? Spots, exactly. So you can see the spot go around. This is also true for low mass stars in general. This is how we do it. As the sunspot goes in and out of view, you can see the light of the star change with time. So we can measure the rotation period of stars that we cannot see the surface. As I said, remember the size on the image was fake. We cannot image the surface of a star. People with like huge infrared, radio telescope and interferometry and these like big arrays like ALMA that you might have heard of, they were able to image the surface of Betelgeuse. Betelgeuse is really close by and it's freaking big.
Yeah.
So we cannot make a photo and see details at the surface of any star practically apart from our sun. So we cannot see the sunspot go around, but we can see its impact on the whole light of the star integrated, like taken all together. It's mush in one pixel on your camera, but you can see it going up and down, up and down, and up and down. This is what Judy does with the telescope here. She sees, you know, light, the change in light when the stars go, her stars pulsate and they become like smaller and bigger and smaller and bigger. So you see the light go up and down and up and down and up and down. Massive stars, they don't have spots because they don't have magnetic fields. How are we going to know how fast they're rotating? There's another thing that we can use, which is called the Doppler, Doppler shifting. Okay, so you know what Doppler shifting is? Right. So if you have light, a source of light coming towards you, its light is going to appear blue shifted towards the blue, and this one's going to appear red, right? So as an object rotates, a part, so I'm a star, right? A part of the light that's emitted on the star, the slit side is going to be red shifted. This one's blue shifted. This one's going to be red shifted. The part in front is not going towards you, away from you. It's going to be no shifted. That's a technical term, no shit. I have to use that for class. My husband used left to rightitude and up to downitude. So we can tell that for stars with basically if you have a spectral line, which is a bit technical, but there's some features in the light of the star that allows us to make that measurement. But if I am a star and I'm rotating, you'd be able to tell that I'm rotating quickly. But what if the star is rotating this way?
Oh, yeah.
Is anything going towards you? Away from you? No. So if they're rotating this way, we can tell they're rotating fast. But sometimes you can have a star that you think is not rotating, but it is in fact rotating fast because it's rotating this way with respect to us. Okay? So it's really difficult to be sure about the rotation of massive stars, apart from the one that do have a magnetic field. Then, because the magnetic field is usually not aligned with the rotation, there's the part of the star that we see, the magnetic field of is going to change with time, the same way as the sunspot go around. So for massive, the only stars which we can absolutely be 100% sure that we measure the rotation properly is those 1 in 10 magnetic stars. But to go back to your question, so there's a little bit of a parenthesis here. Some of them rotate in half a day. Some others have a rotation period of 50 freaking years.
Oh, wow.
I know, it's a very long, so we have everything. So it's not like, oh, only the one that rotates fast have magnetic fields. No, it's mind-boggling. We don't understand. Okay. So I have, we detect magnetic field with polarization. I have some slides, but I'm not going to talk about this right now because that'll be too long. But I want to segue really quickly into black holes. Okay. And the reason we get excited about black holes is that these stars have these big magnetic fields, but massive stars are also losing mass. You heard of the solar wind, maybe? Right? The sun has a wind, some particles that are leaving the sun. Okay, so in principle, the sun is losing mass with time because that wind is going away and it's not coming back, is it? But it's only a tiny, tiny fraction of its mass. It's not going to lose significant amount of mass because the wind is kind of a little breeze, right? Massive stars, on the other hand, have much, much, much stronger stellar winds to the point that a star can lose up to half of its mass during its lifetime because of those winds. But if you slap a huge magnetic field on those stars, some of the wind tries to escape, but gets trapped into what we call the magnetosphere, gets trapped into those magnetic field loops. And sometimes, if the star is not rotating too quickly, it's going to come back to this, keep coming back to the star. And we've observed those things, that gas that is trapped. And we can tell from the spectra of stars. But we kind of made a little calculation, and the most massive O-type star, the star that has the biggest magnetic field in the really hot stars, only 5% of the wind can actually escape for real, for good. All of the rest gets trapped into these big magnetic field loops. And that got us interesting to figure out, like, okay, so this is what I said. Little graph, mass of the star at the start of the main sequence, mass of the star, and mass, at the end of the main sequence. You can see that if you start with 80 solar mass, the winds are going to peel away about, scientists said, with 30 solar mass. It's going to be gone. The star is going to be lighter by nearly half of its weight by the end of its lifetime because of those stellar winds. But if we start to slap a magnetic field on those stars, then the star stays more massive. And that got us really excited when the gravitational wave result came in. This is what made us think about, hey, maybe magnetic star could do something to create heavy black holes. Why do we care about heavy stellar black holes? So black holes that are formed by star, not the one in the center of our galaxies, is because 5 minutes, I can do this.
It's not hard,
Yeah.
you know. We need to go a little longer, it's okay.
We'll just all fall asleep.
That's okay. That's always good. Yes. So every year, there's always a student that keeps falling asleep in class, and it's always that.
But that's what they're supposed to do.
I know, but it's usually only the one, then. Okay, so let me talk about gravitational waves a little bit, because I think that's the most exciting thing that happened in astrophysics in the last, well, it's been, I was about to say the last 5 years, but I think it's been a bit longer than that. So, theory of general gravity, okay? So this is basically Einstein's relativity, where there's a thing called space-time. Woohoo, yes, it is really called space-time. And gravity is basically massive object distorting space-time. And this is what we perceive as the force of gravity. So and Einstein predicted that the existence of those so-called gravitational waves. So what happens is after you have an object that is not more massive, but more dense, the denser the object, okay, so you have the same mass in a smaller volume, will distort space-time more, okay? And this is just an illustration. Space-time is 4-dimension and then so on. And the universe is not 2D, it's just a representation here. But what they predicted is that if you have two massive objects, okay, like stars or black holes or neutron stars that are in orbit around each other, their distortion of space-time combined together as they orbit will create those ripples in space-time. And Einstein was like, we predict that this would happen. We're never, ever going to be able to measure this shit. Einstein was wrong. So there was first some indirect proof, okay, that this could happen. So first, that was Feynman who actually did some math and showed that these waves can actually carry out energies from those objects. Okay, so if you think about power, energy per second, right? So that's kind of related to this quantity. And then these people found two neutron stars. So neutron stars are very, very, very compact cadaver of massive stars. So take the mass of the sun and put that into the size of the Earth, you get what is called a white dwarf. This is what's going to happen at the end of the life of our sun. But if you take that same mass, the mass of the sun, and put it in a radius of about the size of Manhattan, you get what's called a neutron star. Okay, it's a star that is made out of neutrons. Neutrons are not charged. You can pack them very densely. And basically, this is the one possible endpoint at the life of a massive stars. Okay, so what's going to happen to its core? Once it's tried to fuse iron, it's not able anymore. It's going to collapse into a neutron star. And it's the degeneracy pressures. That's a quantum effect that basically is able to stop gravity before the whole thing collapses into a black hole. But they found a pair of these neutron stars that are in orbit around each other. And they were able to measure that the orbit was shrinking with time. So if the orbit shrinks, okay, that means that the system is losing energy. And the energy that was lost, the power per second, was exactly what was predicted for the energy taken away by gravitational waves in such a case. Okay, so there was kind of an indirect proof that these gravitational waves actually existed. But then in 2015, so they've been working on that thing, the LIGO detector for like 20 years or 40 years before that. But this is where they finally turned it on and says, okay, now we should be able to detect those gravitational waves. And that happened in 2015. It was so exciting. And this is what a gravitational wave should look like. So this is a simulation of two black holes. Okay, so that this thing would be the same with neutron stars that are in orbit around each other. The orbit is shrinking because the system is losing energy. And at some point, if they get closer and closer together, they're going to merge together. So notice the characteristic of, so gravitational wave is basically a distortion of space-time, okay, that passes through the Earth, that's coming from these black holes very, very far away. And you notice that at first it has a frequency that then becomes higher and higher frequency, right? The waves are tighter together and the amplitude becomes stronger. Okay? So this is what is expected from a black hole. I'm going to skip this for now. So how are we going to detect? So basically the distortion of space-time, that means that when such a gravitational wave passes we physically extend in one dimension and contract it, and extend, and space itself contracts. How can we measure this? The answer is interferometry. So what happened is you take a laser, you shoot it and you split it towards two mirrors that are quite far away. The beams come back and you recombine them together, which means that if a gravitational wave passes through, I need to press again, it's going to distort space in one direction and make those mirror, the distance between the light source and the mirror, change slightly. Yeah. So what you do then is to keep measuring the distance between those mirrors. And the way they do this is with a laser that has a very, very, very pure wavelength. Okay, it only has the same wavelength. And then when they recombine, it's like a noise canceling headphones. Anyone? Yes. So they combine them so that the wave cancels out. But then when a gravitational wave passes through and changes the distance between the mirrors, then the cancellation is not good anymore and you can see the laser. Okay, this is how they measure those gravitational waves. And Einstein laser was not invented back in those days. So they didn't think that we could measure distances so accurately by using laser and very pure wavelengths. So this is where, okay, little mirrors. How do you know that it's not a graduate student or an undergrad that like stomps next to the mirror, right? Well, the idea is to have more than one of those detectors that are really far away. So there's one in Hanford and the other one in Livingston. And if it's a seismic, like there's an earthquake that makes the mirror move, earthquakes are moving much slower than those gravitational waves, which are supposed to move at the speed of light. Okay, so they need to be nearly instantaneous. It's like a nanosecond, I think, difference between the two. So if you measure the same signal in both detector, then you know it's real. Just to give you an idea of scale, this is the two interferometer. These are 4 kilometers long. And yes, the Earth is round because they actually had, so light goes in a straight line. So they had to actually boost up the bottom, the other bit, because of the curvature of the Earth, right? The laser was not hitting in the right place. They would have made the tube follow the curvature of the Earth. So that's really huge. And then I'm just gonna skip that, but then they turned the thing on after like upgrades and everything, and they detected this in the Washington signal. See the frequency, the oscillation, the amplitude goes up and then nothing. And then they observed the same thing at the other detector.
How soon after it went online did they get the signal?
2 weeks.
Yeah, okay.
Yes, but they've been online, they've been building this for 40 years and like building it and then taking some data, and they were not expected to measure anything, just to kind of keep improving the system and stuff like that. And they were like, this is the time. And I think it was like a week or something like that.
Okay.
So yeah, they detected. And so this specific event, the first one, they were able with the models to basically know that this was two black holes. They're able to measure the mass of each of those black holes separately. So we had 29 and 36, which merged together and created a 62 solar mass black hole.
Wait a minute. Something doesn't add up.
Okay. What is lost? Energy. What's Einstein's most famous equation? E equal mc squared. Energy is equal to mass converted. The mass difference is what's been radiated by those gravitational waves.
Should we clap now?
Very good, very good. Okay. 62. Okay. What blew my mind was 30, 36, 62. Okay. Because measuring the mass of black holes in our galaxy is a tricky business, but we can do it. Okay. So there's some things that are called high mass X-ray binaries in our galaxy. So you have a black hole in orbit with a star. There's some mass that gets sucked by the black hole. Black hole don't suck. If we were to replace our sun with a black hole the same mass right now, what would happen to the Earth? Absolutely nothing. It's the same mass. The Earth is going to continue on its orbit. It's going to get freaking cold.
Yeah.
But the orbit is not going to change. Okay. But these stars, they get really, really big. And then some of the material actually starts to fall onto the black hole because it gets close to the black hole. And then that material spiral and then accrete on the black hole. And as it's going closer to the event horizon, it gets hotter and emit light and X-rays. So we basically have a star, and we know the star is in orbit around something that emits a lot of X-rays. And because of the laws of gravity, if you have two things that are in orbit in each other, you can figure out what mass they are. And if they're very massive, we think, here, we have a very massive object and we cannot see it, black hole. Okay. So we can measure mass of black holes in our galaxy. Okay. But it's really tricky. And this black hole that it just measured the mass very precisely, you know how far it is? 1.3 billion light years away. Our galaxy is 100,000 light years. That's billion light years.
I don't even know what that means.
It's insane, right? So this is the mass of the highest mass black holes in our galaxy that have been measured through binary orbit. Look at the masses. That's in solar mass. There's not a single one above 20. Okay. And then they just discovered a freaking black hole of 30 solar mass and then merged into a 60 solar mass freaking black hole. It was like, we didn't even know that black holes from stellar origin could become so big. So the supermassive black hole in the center of our galaxy are formed in a different way. So we're talking about the black holes that comes at the end of the life of the star. It was like, wait, how did it get so big? Remember what I said about the star, the 80 solar mass star at the end of its life would have lost 30 solar mass? How can we create a 40 solar mass black hole with these things if we're losing all of that mass? And then it kept discovering new black holes. So this is other gravitational wave signals. You can see they're all slightly different, because then it's just a little example of other black holes they found. Some of them here were kind of about the mass that we have in a galaxy, but they found some other like really, really big ones. So that was quite exciting. And when we talk about this, I was like, oh my God, how big of a black hole can we make with the magnetic stars if the wind is not getting in the way? So basically the idea here from these black holes is that they're 1 billion light years away. So they're quite far away. And remember, we're looking back in time because it takes some time for the light to come to us. So back in those days in the universe, there was not a lot of metals, which means, carbon and nitrogen, oxygen, and all that stuff. And it turns out that the stellar winds are more powerful if there's more metal. It's a complicated story, but earlier in the universe, if there was no metal, the winds of massive stars were not as strong. So they would not lose as much mass, so you can make bigger black hole. That was fine. But we were like, ooh, if we can find one of those things in a galaxy, like a huge black hole, magnetic field could be the couple. So we got really excited about this. Yeah. And so I picked this figure last week. So this is a current status. So they keep turning on and off the experiment to make upgrades and learn from, their mistakes and stuff. And this is so everything that's in blue, that's all of the black holes that they discovered through gravitational waves. Some big ones, some small ones, even ones, like even mergers with very different initial masses. It's really, really cool. Excited about that.
So what are the yellows and the red ones?
So yellows are the ones in our galaxy.
EM neutron stars?
These are neutron stars.
Okay.
Because they also find
Oh, I see.
events which are neutron star black hole mergers and neutron stars mergers. These are the neutron stars masses, a collection of mass in a galaxy, and these ones are black holes for which we know the mass in our galaxy, but that are not mergers. And all of the blue and orange are actually the gravitational wave detections.
So what's on the x-axis?
It's cosmetic, I think.
Cosmetic.
Yeah.
Okay. Okay, that looks pretty.
It makes it look pretty.
Mhm.
It's sort of.
But it's pretty cool because now like we have all of that information about black holes that we didn't have before from, not just a galaxy, but, we're talking about billions of light years away. So these gravitational waves is going to be revolutionizing our understanding of black holes, but also the endpoint of massive star evolution. Because these are the result of the life of massive stars. And there's some stuff we don't understand about massive stars. For example, as I said, the magnetic fields, and how is that going to change the life of a star? It's going to make it turn into a different, like maybe it's a neutron star, but if it has a magnetic field, it's going to become a black hole or something like that.
So,
And these neutron stars are actually, I didn't talk about this, but these are the most magnetized object in the known universe. How does that link to the magnetic field of the stars when they were on the main sequence? Is there a link? We don't know. Does it form a different type of magnetic field or these magnetars? We don't know.
so is this what has happened, has happened to population 3 stars? Is that what you're saying? Yeah.
These might not have 1.2 billion light years. That's not going to be pop 3 necessarily.
Okay, I mean, these are leftover from population 3, not. So where are they coming from?
Everywhere. So there's different things, right? So you need to form.
Massive in order to get a black hole that big, it had to be a population 3 star, doesn't it?
Yeah, or something that has very little metals so that
Yeah,
the winds are not
It's
too
the
strong.
same thing,
Yes.
right?
Yeah.
Okay.
Well, yes, I have the students right now doing a master thesis on pop 3 stars, and we had the discussion, and they were looking into, what's an actual pop 2 star versus something that has very little,
Well,
like
very-
extremely metal poor, but they have extremely metal poor stars in our own galaxy, which form, out of pristine.
Right, but
Bubbles
that's
of
population
gas.
2 stars, right?
Yeah, but they're nearly population 3 stars. It's like magnitude.
Right. And it's always the reverse, right? You think population 1's the oldest star, but no, population 3's are. Yeah, right.
Don't get me started. In astronomy, it's everything backwards.
He said something in the chat about cosmological archaeology.
What?
I don't know what he said.
He said the universe isn't old enough to form a black hole.
Black holes.
There was also another question about, the radiation of the gravity wave. It goes out in all directions.
Yeah.
You might want to correct that in the chat. Go to the chat.
So gravitational waves are going to come out like in a ring or like a sphere around the object, right? But when it's 1.3 billion light years away, when it arrives to us, it's nearly so you do telescopes, right? The rays of the sun and the stars, they're all coming parallel to each other, even though when they exit the stars, they're going in all possible directions. But we're so far away that from our point of view, we only see the ones that are nearly all parallel to each other. Same thing for gravitational waves. If the gravitational waves was coming from, the sun or something very close by, then you would see kind of the curvature of that wave. But because they're coming from so far away, from our point of view, it's nearly a plane, like a straight when it passes through here. Yes.
Black hole conspiracy theorists.
Oh, there.
Yes, so they were thinking about the LISA. So I'm not an expert in this, but the LISA, which is supposed to be an array of satellites, but then it's sensitive to different type of gravitational waves. Oh, what they were talking about. So imagine you have a neutron star and there's a little mountain on it, and the whole thing is rotating and the mountain is turning around. In principle, it changes the distribution of mass, and that should also create gravitational waves, which anybody ever read Dragon's Eggs? An old sci-fi book from the 60s about the population of little being that lives on the neutron star. Oh, that's pretty cool. They can only go in one direction and then the other one goes to the magnetic field. That's pretty cool. I know, it's pretty cool. Yes, but it depends a little bit. There's like the price of those little beings. But it's, the scientific concept, I figured, those are the questions.
Yeah, is there any directional information about that comes out of these experiments in terms of to the point that you could have 2 detectors that would triangulate?
But to triangulate, how many do we need?
3,
right? So at first, I think I might have deleted those slides when I made some. Oh yes, there you go. Cool, I have the slides. So at some point there were only 2, okay? Which means that they could only, I had a better slides for this. So if you have cell phone towers, right? cell phone towers, and you ping. If you have 2 towers, you can basically tell whether it's coming from this direction or this direction. So if you have only 1 towers, it tells you how far you can be, but you don't know where. If you have 2, then you can go left or right, but then if you have a 3rd one, then you can actually triangulate the position, okay? So that's why at first, with only the 2 detectors in the US, they had a really, really large bed, it's the Milky Way, right? So they could locate with a really large, or with a large bed, so there's no way of figuring out what's gonna go, what's going on. Also, if you have 2 black holes that merge together, are you expecting anything in regular light? We already don't see a black hole, so if they merge, we don't expect what they call the electromagnetic counterpart. But if you have 2 neutron stars that merge together, well, there's actually matter, right? It's not a black hole, so we expect a bit of a kaboom, okay? But then we couldn't figure it out because it's really a really large area in the sky to search. But at some point, the Italians joined the party, and they put there's another, the Virgo Observatory, which is in Pisa.
Pisa is not really known for building stuff real straight. That tower is straight. Whatever the word is. Yeah. Orthogonal.
So really cool, okay? Gravitational wave detected by the 3 observatories. They know it's a neutron star from the gravitational wave signature. They know the massive. They said this is neutron stars. 2 seconds later, the Fermi NASA satellite detected a gamma ray burst from the same general location. At that point, if somebody paid attention to where the telescope of the world were pointing, they probably knew that something big was going on because every telescope went, because now they had 3 telescopes, which means they could triangulate the position in the sky better. Okay, and then all the telescope went, let's look at that, right? And then they found what's now called a kilonova, which was about 10 hours later, which is what they expect from the simulation. If you have 2 star neutron star merge, there's going to be like a big cloud, and at some point, photons break free. And they found this object right here, which looks like a supernova, but is not as bright as a supernova, so they call it a kilonova. And what is cool about this is that, remember when I said that massive stars made everything? I kind of lied a little bit, because there's things that cannot be explained by massive stars. Platinum, gold, massive stars on their own cannot create enough of those. Okay, and you could say that, well, that's larger than iron, and massive star cannot fuse iron. I know, but when there's a supernova, there's a lot of neutrons that fly all over the place during the explosion, and those neutrons hit, for example, iron. The neutron goes in, so you get an isotope, and then that one of the neutrons gets unstable, turn into a proton, and then you get these higher up elements. So you need to bombard stuff with neutrons. But they're saying like massive star cannot make enough. But they theorize that if you merge 2 neutron stars together, you can make up for what was missing. Okay, so they took a spectrum of that thing. What do you think they found? Found spectral line of, or not, it was not spectral lines, but it was like the distribution of energy that said this thing was full of gold and platinum and nickel and so on and so forth.
Let's get it.
Yeah.
So yes, triangulation, very important. Anything else?
What made the light take so much longer than the gravitational wave?
One would think because light travels at the speed of light, right?
Certain things
But
can slow it
then
down.
you need the light can be, if you have something that's really dense, light can actually take some time because it's bouncing back and forth on atoms, for example. So gamma rays can fly a bit in straight line because they're more energetic, they don't interact. But you might know about this. So the light, how long does it take for a photon, particle of light created in the center of the star, of the Earth's sun, to get out?
8 minutes.
1,000 years.
It is not 8 minutes. 8 minutes. We're gonna come back to this 8 minutes in a second, right?
8,000 years.
But to get out of it, it's like, okay, you're trying, you're gonna call it the drunken way. That's right. I'm trying to walk out of a bar at their park on St. Patrick's Day. And you go and just like make a step. Oh, and you keep like taking a random walk. Eventually, you're gonna get out, but it's gonna take you much longer than if you were walking into a straight line. This is what happens to photon in the center of the sun because it's really dense. So photons try to escape, but they keep bouncing off the atoms and going, and then eventually they slowly make their way out. But then, once they reach a point where they're able to take a step without, and each of those steps are at the speed of light, right? But it's just bouncing. But at some point when they stop bouncing, they can escape free. And this is when it takes the 8 minutes to come from what we call the photosphere of the sun, when the photons finally can go free. It takes 8 minutes to come to us, but it took them thousands and thousands of years to escape from the center of the sun. Same principle here with the what you're expecting the electromagnetic counterpart of these mergers is that it takes a bit more time for light to be able to break free of the dense object.
So I still don't quite get that because the whole object is blowing up, right? All through it, the surface as well as the center, because it's really blowing up. So the light from the outside should get to us about the same time as the gravitational wave would, unless there's.
And I think that some of that light is actually radiative decay as well. So it's photons from all of that heavy element decaying into. So it's the same for supernovas as well, right? I think that the early light, and I'm not a supernova physicist. So it's gonna be fun if my colleague Fed is watching this. Correct me later on the comments, right? So a lot of the power of supernova light comes from radiative decay of nickel, and that takes some time.
That makes more sense because the gamma rays are technically radiative radiation as well.
Mhm.
And they just took
Absolutely.
2 seconds.
Yeah.
2 seconds, but the regular light took 10 more hours.
Mhm.
Yeah, don't forget the speed of light changes depending on the wavelength of the medium, too, right?
Yeah, but it's not a big.
Well, what medium is it going to?
Vacuum.
Yeah.
No, it's mostly going to vacuum, but inside of the object, like the same as the sun, right? It takes some time for the photons to get out.
He's gonna make a joke here. Only air and space.
I never miss a chance.
You know the joke that he's referencing.
No.
You got it.
Well, it's all the air in space that's slowing down the light, no?
Actually, it's not that empty.
She's not being it to me.
Hey, Jeff, I didn't know there's air in space.
Oh, because they've got an air and space museum. Thank you, Bill.
I'll have to try that.
So normally they say there is no air in space, and then I would say, but then why do they have an air and space museum?
Who's seen Interstellar?
Yeah.
Every time.
You've seen Interstellar?
Wonderful.
So do you know that the rendition, that's why I had a photo of what you
Yeah.
earlier.
Yep.
So are we seeing gravitational waves going on?
So not in there, but do you know that the black hole rendering in Interstellar is actually real physics computation?
Yeah.
So
Kip
it's
Thorne.
not somebody who drew this, right? So the same person who was doing those thing for Interstellar also made the calculation for what it would look like
Interstellar
Or-
2.
gravitational. So what we would see if we were able to see to resolve the event horizon of the two black holes. What you're seeing at the back is the light from the stars and the behind, and then that's a distortion of space-time around the two black holes as they're merging and they're coming in and coming in. So that's pretty cool. And then you can see the.
Wow.
So I thought it was pretty cool. But also, do you want to, oh, did I put them in? Yes, do you want to hear them?
Yeah.
Because those waves, if you, so sound waves is compression of air, right? As I'm speaking, something is vibrating. And it turns out that the frequencies of those gravitational waves, if you transfer that into air waves, it's about in a pitch that we can hear. So what do you expect? The frequency needs to get higher and the amplitude needs to get louder. So let's see if I can actually play this.
Sounds like that.
Give me a second. I might have to mute this one. Sound. Actually, there was not too much feedback, so I might be able to put my sound on. Not feedback.
Yeah, somebody else could be moved.
1 second. Does this one, how do I put the sound down?
Down, let me take a
Oh,
look.
here you go, I found it.
Does that work?
I think it worked. I'm going to put the sound in here.
No feedback? No feedback? Perfect. Okay, let's see if I can play this.
Oh,
That's great.
Okay.
Okay,
Put that back. Mute this. Put the sound back on this one. There you go. Okay, so the second one, they actually double the pitch so that you can hear it a little bit a little better. And then you can tell the more massive black holes are the one that finish with the higher pitch and the higher amplitude. So the one that go whoop, or more massive black hole than the one that goes whoop. And you can have ringtones. There is an alert, an app that would give you alerts when there was a gravitational wave detection published, and then the alert sound was actually the what they call the chirp of the gravitational wave. So that was pretty cool. Yes.
Very good.
Véronique, thank you again very much. And just in closing, again, everyone, I suggest keep an eye on the groups.io for all the activities that are happening between now and the next meeting. Register for the dinner meeting, even though there's no speaker, it'll be someone fantastic. And there are refreshments, so if anyone would like, please join us in the library. And again, Véronique, thank you so much. That was fantastic.
Sorry, it was a bit long.
That's okay. All right.
Nobody was falling asleep, so I didn't have a cue.
Oh, yeah.
I think that's
Okay.
what's happening. I think it's focusing on the closest object. Yeah. Except the closest object.
So Rob, I just hit end and then do save, right?
Hit the stop recording, the stop button at the bottom. See the little square?
Nope.
Stop recording.
Oh.
Every other day or.